I think this is going to be about the last of my epsilon delta proofs, at least for now. The last one I want to get to is, let's do a trig one. So let's try the limit as x goes to a, sine of x equals sine of a. Now, earlier in this, I don't remember where it was. Oh yeah, when we were proving sine of theta over theta, we came across an inequality that was like this. Well, if you use, or if we rewrite this way, when theta goes to 0, sine of theta is forced to go to 0 by the sandwich theorem, or the squeeze theorem. So, I already know this much. Let me change that a to a 0. Actually, better yet, we know that equals 0, which also happens to be the sine of 0. So I've got it for 0. So let's work with some other things then. So I'm going to let's assume that a is between negative pi over 2 and a does not equal 0. So in this region here then, if I'm between negative pi over 2 and pi over 2, and I'm not equal to 0, that means sine of a is not going to be 0, and neither is cosine of a. It would only get to 0 pi over 2. Why am I doing this? Well, because if you look at the sine function, I'll just draw a really simple graph of this. From negative pi over 2 to pi over 2, we span from negative 1 to 1. All you need is this part of sine to do anything involving sine over any interval. Because this piece, when you go to the next version of it, it comes down like this. This piece that I just drew from here to here is identical to from here to here, except it's just reflected, it's just turned around. So all the same rules are going to apply. If I want to, I can put a between any odd multiple of pi over 2 and the next odd multiple of pi over 2. And I can still handle the 0 parts. That's not going to be a problem at all, because just like up here, we'll have what we need. So I only need to worry about that particular spot. 0 is already handled. So let's take a look. Like everything else with these proofs, we're going to let epsilon greater than 0 be given. Now what we're going to look at is the absolute value of sine of x minus sine of a. Now x is not going to, remember, x will not equal a. It does not equal a. That's the nature of limits. X is not exactly equal to a. So, I guess though, then a could actually be 0 and we'd be okay. But I thought I would separate that case anyways. If x is not equal to a, then x minus a does not equal 0. And what I want to do is let h, the letter h, equal x minus a. Or what's better, so h is going to measure the difference between x and a. And otherwise, h plus a equals x. That's kind of the way I want to look at it. So when I grab this absolute value again, sine x minus sine of a, I can rewrite this as sine of a plus h minus sine of A. Later in the semester, or later in the course, we will do this kind of thing all the time. But the reason why I want to work with this, is because I can take and split this up. Sine of A cosine of H plus sine of H cosine of A minus sine of A. Then let me gather some things and do a little factoring. We have sine of A times cosine of H minus 1. What I've done here is I've taken this guy here and the negative sine of H, put them together and factored out a sine of A. Sine of A plus sine of H cosine of A. Now H, keep in mind, from this, since x is going to A, this implies that H is tending to 0. That's important. I'm going to use the triangle inequality to break this up into less than or equal to the absolute value of sine of A times cosine of H minus 1 plus sine of H times cosine of A. Now I'm going to continue with these absolute values. I'm going to break them up into more individual pieces. So I'm going to put an equals here since I'm not changing the value of anything. I'll have the absolute value of sine of A times the absolute value of cosine of H minus 1 plus the absolute value of sine of H times the absolute value of cosine of A. And you'll see in a minute why it was so important for me to have x does not equal A. I don't want a 0 happening in there. Now let's take a look at some of these things. When I was first doing sine of H over H, the limit as H goes to 0 equals 1, or sine of theta over theta, the limit as theta goes to 0, turned out to be 1. I made use of a picture that had a circle of radius 1 and had an angle. What I'm going to do in here is I'm going to use H this time. And if you'll remember, I draw a line straight down that the base of this triangle was cosine of H. And the circle was of radius 1. So the piece that's between cosine of H, between the length of cosine of H and 1, the piece in there is 1 minus cosine of H. Now, there's a variety of ways I can do things here, but I'm going to be more, I think I'm going to go more with an obvious way of looking at it. As H is going to 0, this piece is coming down. That means cosine of H is getting bigger and approaching 1, which means 1 minus cosine of H is approaching 0 as H approaches 0. What that means is that there is a delta 1 greater than 0 with the absolute value, let me get rid of that, 0 less than the absolute value of x minus A less than delta 1 implies that the absolute value of 1 minus cosine of H can be made to be less than epsilon over 2 times the absolute value of sine of A. A is a given number, sine of A is simply a number, and we know it's not 0. All right, on the other hand, we know that sine of H, in the same picture we had here, this piece here was theta in the original part. That part was originally theta. Here it's H. It matches the angle in here. So, and we can see as that goes to 0, or we even had done sine of h was less than or equal to the absolute value of h, which proved that sine of h goes to 0 as h goes to 0. I think I just repeated myself from what I said earlier. No, I didn't. Okay. So, come back down. Since this is true here, there is a delta 2 greater than 0 with 0 less than the absolute value of x minus a less than delta 2 implies that, I'm sneaking a peek, I know what I need now, the absolute value of sine of h could be made less than epsilon over 2 times the absolute value of cosine of a. Remember, that's not 0 either. I probably could have been a little more intelligent with what I did, but what I'm trying to do is kind of just work my way through with as little trickery as possible. This thing already has some trickery. So let me grab this piece here and this piece here. Let me rewrite them and put in my possible deltas and epsilons and all that kind of stuff. So we could simply say let delta equal the minimum of delta 1 versus delta 2. That guarantees that my two inequalities will be satisfied because this one works with delta 1, this one works with delta 2. Any smaller ones it will work with. So let me go ahead and write what I have up there. I have the absolute value of sine of x minus sine of a was less than or equal to, we can sneak a peek again, sine of a times cosine of h minus 1. So the absolute value of sine of a times the absolute value of cosine of h minus 1 plus the absolute value of sine of h times the absolute value of cosine of a. Now let me go ahead and put in my inequalities that I have here. I have the absolute value of sine of a, and actually this should be strictly less than, because those inequalities up there were that. The cosine of h minus 1 was less than epsilon over 2 times sine of a. And you'll see why I chose what I did. It's epsilon over 2 times the absolute value of sine of a. And then the other one, the sine of h was less than epsilon over 2 times the absolute value of cosine of a times the absolute value of cosine of a. Hopefully you see it coming. The sine of a's cancel, cosine of a's cancel, and we're left with epsilon over 2 plus epsilon over 2, which equals epsilon. And that completes proof. So I'm not going to do any more proofs. I think epsilon delta proofs. I think I've exhausted all the ones that I want to do yet, except later on in the course we will be dealing with exponentials and logarithms. So can't wait for that.